Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the relationships between properties of gases. So remember, there's those four properties of gases: volume, pressure, the amount of gas, as well as the temperature. So I'm going to go through various relationships and how they're related to each other based on the ideal gas model. Okay, so let's get into this. So the first relationship I'm going to look at is the relationship between volume and pressure. So what we notice when we look at the volume and how it's related to the pressure of a gas, of course, we're going to keep temperature and the amount of gas constant. So this relationship only holds if the amount of gas we're dealing with is kept constant and the temperature of the gas is kept constant. So those two have to be constant in order for this relationship to actually occur or to be in effect. Okay, so what we notice is that when you decrease volume, pressure will increase. And if you increase volume, pressure is decreased. Well, why is that? So we got to go back to the relationship of the definition of gas pressure. Remember, pressure is the amount of force applied through a given surface area. So pressure is equal to force over area. And when we're talking about gas pressure, we're looking at the force that is applied due to the collision of particles against the wall of the container, and the area that we're looking at is the area of the walls of the container itself. So what happens when we decrease pressure? So here we're going to start with decreased pressure, and here's a little model that I have. So you're going to have to imagine what happens. So here I have a container, and on the top here I have a piston that's movable. And so here I have a few particles, and they're moving in various directions in the container. Excuse me. And so here I have a certain volume, and at this particular volume, the particles are hitting up against the wall at a certain amount and therefore applying a certain pressure here. So what happens when I decrease the volume? Well, I can decrease the volume by lowering the piston to halfway, right? So here I have it. So I'm going to lower the piston. And then what you notice right away is that the particles are now bunched up closer together. So they don't have as much space to move around. There's less surface area here. And so you have more particles that are closer to the surface of the container at any one moment. Here, when they're farther apart, there's more space, there's more area, so less particles are close or even hitting up against the sides of the container at any one moment. When you decrease the volume, you decrease the surface area. So you have, at any one moment, you have more particles hitting up against the sides of the container because there's less area to move around. There's less area, so more particles are going to hit up against the air, hit up against the walls at any one moment. We didn't increase the amount of particles, but we have increased the amount of collisions happening at one moment on the surface because now there's less surface. So how does this fit in? So with regard to the number of particles colliding against the wall at any one moment, that has increased. So the top part is increasing. So that increases gas pressure, but also the area of the walls that we have has decreased. So decreasing the denominator here also increases gas pressure. So what's going on, right? So let me recap. So we decrease the volume. So we're going from piston up here to piston down there. So this increases the number of particles per volume of the container. So we have the number of particles colliding with the surface area plus we've this volume has decreased, or the volume of the container has decreased. So this ratio of number of particles per volume has increased. How has it increased? Well, we've increased the number of particles that are close to any area of the wall. So the number of particles colliding with the wall at any one moment has increased. And so what does that do? That increases the number of collisions per second, right, per area of the wall. The number of collisions that we are happening faster because there's less space to move around in, so you get more collisions per given amount of time. So here, the number of collisions has increased, and the area of the wall has decreased, right? So we've increased this ratio. And by doing that, we've increased the force due to the collisions, right? So remember, the number of collisions that's happening during a given amount of time, at any one moment, we have more collisions up against the walls of the container. That's going to increase the amount of force, right? So the more particles hitting up against the container, more force. And we have the area of the container. As we see, the area, the surface area available has decreased. So this ratio has increased. And because this is pressure, if we increase this ratio, we're increasing pressure. So decreasing the volume increases the pressure. And so what we know now, so if I add to this, this has an inverse relationship. According to the ideal gas law, or ideal gases, the decrease in volume and increase in pressure, this has a inverse proportionality to it. So what does that mean? So if the, how should I say this? If the temperature and the amount of gas is held constant, then pressure, or I should say volume, is going to be inversely related to pressure. Or we could do it the other way. Pressure is inversely related to volume. Yeah, so pressure is inversely proportional to volume. So in this case, if we double the volume, right? If I double the volume here, if I put a 2 there, if I double the volume, then what happens to pressure? The pressure is now 1/2, 1/2. So whatever I do to the volume here, I do the opposite to the pressure. Doubling the volume halves the pressure. If I was to half the volume, then that would double the pressure. So they're inversely related to each other. Okay, and so this allows us to formulate a law known as Boyle's law. So Boyle's law, since pressure and volume are inversely related to each other, then if I put volume and pressure together, right, if I multiply volume on both sides, that cancels out, and now V times P is proportional, is going to be proportional to some, this is not 1, but this is going to be some constant, proportionality constant for this relationship, volume times pressure. And so that gives us the Boyle's law. So the volume that we start with multiplied by the initial pressure that we start with, V1, P1, is going to be equal to the volume that we end with multiplied by the pressure we end with, P2 V2. And so this, ladies and gentlemen, is known as Boyle's law. So basically, Boyle's law says that if you change the volume of a given gas, then the pressure will change inversely. So in order for this to be true, this has to be true here. These sides have to be equal. So if I double the volume, then in order to keep this equal, then the final pressure that I have has to be halved. If I double the pressure, then I have to half the volume, right? So this is Boyle's law. So that's one of the relationships of between gases, between the properties of gases, volume and pressure. So now let's go to the next relationship between our properties of gases. Okay, so now let's go over the next relationship, which is the relationship between pressure and temperature. So when we look at the, excuse me, when we look at the relationship between pressure and temperature, we notice that when you increase temperature, that also increases the pressure of the gas. If you decrease the temperature of the gas, then that also will decrease the pressure. So we know this from experience. And so what we see here is a direct relationship between the two. So as one goes up, the other one goes up. As one goes down, the other goes down. So how can we explain this? So again, we go back to our relationship, our understanding of pressure here. Pressure is equal to force due to collisions of the particles onto the side of the containers and the area of the walls. So pressure is equal to the division or the relationship between force and area. And so if you look at my picture here again, here we got two containers with a piston again. Notice that the piston is at the same place, so we're not changing the volume. So in this case, for this relationship to hold, the volume and the amount of gas now have to be constant. So this relationship will not hold if you change the volume or if you change the amount of gas. So both of those have to be constant in this situation. So keeping those constant, we're only going to change the temperature. So here I have low temperature particles. So the gas is at a low temperature, relatively low temperature. And what you'll notice here is I have the same number of gas particles, but the arrows given in blue because this is cold, right? So the blue arrows are shorter, not as long. And so that indicates that these particles are not moving as fast, right? So if the particles are moving slower, then that means that when they hit the wall, they're not going to apply as much force, right? So take the example of a tennis ball. If I take a tennis ball and I throw it against the wall, if I just throw it gently against the wall, then it's going to hit the wall softer and therefore apply less force to the wall. But if I throw the ball faster, then it'll hit the wall harder, therefore applying a greater force to the wall. Okay, so it's the same thing with temperature. So again, according to the kinetic molecular theory of gases, basically temperature and the speed of gases are directly proportional. So increase the temperature, then you're going to increase the average kinetic energy. Well, what is kinetic energy? It's 1/2 mass times velocity squared. So it's related to the speed of the molecules. So if you increase temperature, you're going to increase the speed of the molecules. So at low temperature, they're not moving as fast. So when they hit the sides of the container, not going to affect anything. Oh, I'm sorry. When they hit the side of the container, it's going to hit the container with a certain amount of force. But if I increase the temperature, then the particles are going to move faster. They're going to hit the sides of the container harder and therefore apply more force to the container and to the walls. Okay? So if we look at this, if we write this out, then what happens? We increase the temperature. Increasing the temperature will increase the average velocity of the particles. Why? Because temperature and kinetic energy are related. Kinetic energy is related to speed or velocity of particles. So increasing temperature is going to increase the average velocity of the particles. So this is going to have two effects. One, this increased average velocity of particles is going to increase the number of collisions. If particles are moving faster, then you're going to have more collisions per second in a given amount of time per second, right? So higher velocity means increased number of collisions. The second thing is you're also going to have an increased force of collisions. The particles are hitting the wall harder. So therefore, the force of the collision is going to be higher. Therefore, on both accounts, you're going to get an increased total force of collisions. More collisions, which is increasing the force, and harder collisions, meaning the force of each collision is greater, and so therefore increased total force. So that means that in this relationship here, F over A, the area doesn't change. That stays the same. Because the volume doesn't change, the area that is available to the collisions is the same. So that doesn't change. So the denominator stays the same, but the overall force increases. Therefore, pressure increases because pressure is equal to force over area. And so that's how you explain the relationship between temperature and pressure. Okay, so with that, we have another law that we can introduce you to called Gay-Lussac's law. So based on this, we can see that pressure is directly proportional to temperature. So pressure is directly proportional to temperature. And again, we can, if we divide both sides by temperature, then basically this cancels out and gives us 1, but this is a proportion. Again, we're going to get a proportionality constant. So pressure over temperature is going to be equal to some constant. And so this is where we're going to get, in order for this to stay the same, if we change the pressure, then the temperature has to change in the same way. If we double the pressure to keep it constant, then the temperature must be doubled as well. So again, those would cancel out and you get the same constant. So what does this give us? It gives us P1 V1 is equal to P2 V2. So the P1s and the V1, that's what we start with. So if we have a gas that we have a certain initial pressure with, and we have an initial volume of that gas, if we change the pressure or the volume, then we can find out what the new volume or pressure is. So that's what the P2 V2 is. So pressure, the new pressure, and the new volume. So if I change the pressure from one thing to another, and I know what the original volume was, then I can use this equation to solve for the missing volume, the final volume that I need to find, or whatever it is I need to find. So this is Gay-Lussac's law. Okay. I think Lou-Sachs law. So Gay-Lussac's law. P1 over V1 equals P2 over V2. Okay, let me double check to make sure I spelled that correctly. Yes, I did. So let's move to the next relationship. Okay, welcome back. Now we're at relationship number 3, and I forgot to change that to a 3. Okay, this is real time. Okay, so the third relationship is between volume and temperature. So when we look at the relationship between volume and temperature, we're keeping the amount of gas constant, and we're keeping the the amount of gas and pressure constant. So the pressure is going to stay constant, and the amount of gas is going to stay constant. So let me explain how this is going to work. So we notice that when you increase temperature, volume is going to increase. So again, this relationship only holds if pressure is constant and the amount of gas is constant. Otherwise, this doesn't hold. Okay, so if the amount of gas is constant, if the pressure is going to stay constant, then if we increase temperature, then the volume is going to increase. If you decrease temperature, then the volume will decrease. So there is a direct relationship between temperature and volume. So why is that? So let's go ahead and look again at our definition of pressure. So pressure is, again, force divided by area, the force due to collisions of the particles divided by the area of the walls of the container. So how much force is applied to a given area. So what happens when we increase temperature? So temperature is increased. What does that do? So like before, that's going to increase the average velocity of the particles, the average kinetic energy, and the average kinetic energy is related to the average velocity of the particles. So increasing temperature increases the average velocity of the particles. Once again, if you increase the velocity of the particles, that's going to have two effects. It's going to increase the number of collisions because the particles are moving faster. You're going to get more collisions per second. And since they're moving faster, they're going to hit the sides of the container harder. Therefore, each individual particle will be applying a harder or greater force to the side of the container. Add these together, it tells us that the initial increase, there's going to be an initial increase in the force per area, force per square inch or force per area, which means, as we know that force per area is pressure, therefore the initial pressure is going to be increasing. Now wait, hold on. You're going to say, Mr. Koval, didn't we say that this is only going to work under constant pressure? Well, that's what we mean here with our picture here. So we have a movable piston. This piston is free to move. And so the pressure initially is going to go up, right? But if the particles are going to be applying a greater force when they hit, and this piston is able to move, then the greater force is going to cause the piston to move up, creating more volume, right? So what happens when the volume increases? What happens to pressure? Pressure decreases, right? So the initial pressure of the container is going to go up, but because we have a movable piston that can change the volume's going to change. The volume's going to get bigger because these are hitting harder. And so therefore, the pressure is going to go back down to what it was before, which is equal to the outside pressure. So right now, here at this low temperature, the pressure of the gas inside is equal to the pressure of the gas outside. But what happens when we increase the temperature? We increase the temperature, as I said, increasing the temperature increases the average velocity of the particles, increases collisions, increases the force per collision, and then that's going to increase the initial force per area, which is then the pressure. So the inside pressure is going to increase. That inside pressure is going to be greater than the outside pressure. It's going to push the piston up. It's going to cause the container to expand in a manner of speaking. And then therefore the inside pressure is then going to decrease until it's equal to the outside pressure again. So now the pressure is back to where it was, constant. And then therefore, in order to do that, that means the volume increased. So the volume had to increase to get the pressure to stay the same. So that is how temperature and volume are related. They're directly related. And this brings us to another law, Charles' law. So what we have here is, again, pressure is, again, directly proportional to volume here. If we divide both sides by, not pressure, volume and temperature. So volume and temperature are proportional, okay? So we're going to get temperature and volume are directly proportional to each other. So if you increase one or if you double one, then you have to double the other. And we can see that again by dividing both sides by temperature in this case, right? So, and then these cancel out, becomes one, and then you end up with a proportionality constant again. So you have volume over temperature is equal to some constant, we'll call it K. So in this case, again, if I double the volume, in order for it to stay constant, the temperature has to double. So doubling the volume will double the temperature. Doubling the temperature will double the volume, right? So then that will cancel out and you get the same thing you got before. So it's constant. So this gives us the relationship of V1 over T1 is equal to V2 over T2. And this is Charles' law. So Charles' law basically says that volume and temperature are directly proportional. So Charles' law. So basically what this is saying, just as the other laws, if I have an initial volume of my gas with an initial temperature, if I change one of these two, if I change the initial temperature or volume, then the other one will change accordingly. So let's say if I have an initial volume and initial temperature and I change the temperature to something else, that other temperature is at my T2. So I change the temperature from some temperature to another temperature. That's the other temperature. The new temperature is my T2. And so then that my new volume has to be something, and I can solve for that. I can predict what the new volume is going to be. And so this is Charles' law. So that is the other one. So that's three laws. So Charles' law, we've done Gay-Lussac's law, we've done Boyle's law, we've got more laws. So stay tuned to my next video. So in my next video, I'll be going over the rest of the laws and the relationships between the different properties of gases. If you enjoyed this video, then please go to the next one and watch the next one. Please like the video, share the video. If you learned anything from this video, if you like this video, then hit that like button. Also, make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, if you have a question or a problem you want me to help you with, put that down below. I'd love to help you with that. Thanks for joining me and have a great day.